5 people come in for math help, and there are 12 desks. And how many ways can they be seated? And I find this question in particular causes some problems because I see students making 12 spaces because you're used to putting students into desks. So it makes sense that the space is a desk. But we have to remember that the spaces are decisions. And in this case, there's only 5 decisions because person 1 comes in, they have to decide where they're going to sit. Then person 2 makes a decision, 3, then 4, then 5. And since there's 12 desks, that's how many choices we have for person 1. And then person 2 comes in, and how many choices do they have? 11, right, because it's very awkward if you come in for math help and decide to sit on somebody else's lap, right? So we'll go with 11 there, otherwise it's like awkward. And then 10, and then 9, and then 8, and this is the same as 12p5. So remember in the permutation notation that the 5 is sort of like number of decisions, number of spaces, and 12 is the choices you start with, or the number that you start with. And sometimes that notation is nice. For example, in here, there are 32 desks, and there's 20 of you. So if I said, new seating plan, everybody in the hallway, first person walk in, sit wherever you like, next person, no sitting on laps and blah, blah, blah. Then in this case, first person would have 32 choices, and there would be 20 spaces. So in this case, it's nice to use the notation, because then we don't have to write out all those 20 spaces, all those decisions that need to be made. And if we type this into our calculator, under probability is NPR, we can do 32p20, 5.4933185339E26. I'm going to write this. Do you know what that E26 means?
Times 10 to the 26.
Times 10 to the 26. So we write out what this number actually is. Equals 5, 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 25, 26, approximately. They wouldn't all be zeros. So since we don't know what the digits are, we'll have to just give you an idea of how many different seating plans were possible. So one year, I had a contest. I put a random seating plan on my computer, and I said, if anybody guesses the random seating plan correct, 100% in the class, don't have to write the exam, don't have to come again, you just get 100% in math. So there, everybody was excited. So first person guessed wrong, and then the next person. It actually had advantage going later, because if Jonathan got the first one right, you were like, okay, at least I know that much. But I don't know if this was mean. You can decide yourself. But I decided on one kid I was just going to be like, yes. Even though they were totally wrong. But every name they said, I was like, yes. And they went through the whole thing, and I'm like, you got the whole thing right. And I was like, I'm just kidding. Does that mean? I mean, look at the chances of getting it right. Practically impossible.
Why don't we go and do every single one right now?
Write them all out and pick one of the seating plans from that. That would be a good use of time. We have done, and I'm actually going to get you to change this to the textbook. I like their wording better. Change that to identical objects. If you have identical objects, like egg, you count all the letters, which is 3 factorial, and divide by the identical objects. So ask the city, 1, 2, 3, 4, 5, 6, 7, 8, 9 would be 9 factorial. We have 3 S's, 2 I's, and 2 P's. That would be the number of ways you could rearrange the letters. And so one of the things we have to get good at is recognizing when something is an identical objects question. Contractor sold model homes of type A, B, and C, 3 of model A, 4 of model B, and 2 of model C. Can we we see that this is an identical objects question. Have you ever driven in a neighborhood where a bunch of houses look the same? They change the front, like one of them's white and one of them's blue, but like the style of the house is exactly the same all the way through. Very typical. And I guess different periods of time might not be. Uh-oh. 3 of Model A, 4 of Model B, and 2 of Model C. So this is like a Mississippi question, except our word is ab. So if you did this, there's 9 letters, which would be 9 factorial divided by 3 factorial, 4 factorial, 2 factorial, and you would get your answer. So this was one way of seeing an identical object question. Identical object question, we're going to learn a new strategy today, which is called the grouping strategy, which sometimes you can get these two strategies mixed up. So we have to say, do I have objects that are exactly the same? If they're exactly the same, it's like a Mississippi question. And here's another question of these directions. John lives north and 6 blocks east of school. So school's here. Is that right? John lives north, east. This is John here. There we go. He's going home from school. How many ways can he do this? So one way that we can do this is we can represent, we know that to go home he has to go north 3 times and he has to go east 6 times. In this situation then, how you rearrange where those easts are, where those norths are, each one represents a different path. So we could do this by 9 factorial, 3 factorial, 6 factorial, which is equal to 84. But remember, we could also do this with counting. So if I'm starting here, each of these dots, there would be only one path to get there. And in fact, anything in a straight line, like even all the way to this corner, there's technically the only way that it could get to that corner is that straight path. Same thing up here, these would all be 1s as well. But we could get to this path in 2 ways by adding 1 plus 1. 1 plus 2, this would be 3 ways and 3 ways. 1 plus 3, 4. 3 plus 3, 6. 4. 1 plus 4 would be 5. 10 and 10. 20, 15, 6, 7, and 21, and 35, 56, and 28, and sure enough, it works out to 84 that way as well. So we could count it out, and sometimes the counting it out is important, especially if we add a restriction. Like, for example, this is where Susie lives. And now, for whatever reason, when John walks home, he always goes past Susie's house. How many ways can this be done? So can you see now that, like, for example, these places here, he'd never walk there again, and he would never walk in those places again. Those would be taken out. And if we erase the numbers above, which numbers, I have to erase some of these numbers. Now I can keep the 1s and I'll erase these ones. How many ways can he get home now? Well, this would still be 2, and this would still be 3, and this is still 3, 4, and 5, and this is 6 and 10, and there would be 15 ways that he could get to Susie's house. But then what number would I put here? And what numbers would I put here? Do the same sort of thing. How many? This would be 15 plus. There's no way he's coming from this direction, so that's 0. This is still going to be 15, 15, and 15. 30, and 45. So if Susie lived there, there would now be 45 ways that John could walk home from school, making sure he goes past Susie's house. Now we could add a new twist to this, and that says, something has happened, and John has to walk home from school, but he is not allowed to walk by Susie's house. Now we have the not strategy. Can you see the number of pathways that don't go through this point would be all of them 84 minus the 45 that go through that point. If you take away those 45, what would be left would be all the pathways that don't go through that dot. So we can add different restrictions, which makes the question a little bit harder, but we can still use our counting strategy to figure it out. All right, next strategy is the grouping strategy. Sometimes you want to rearrange things, but have them in certain groups. Maybe in your room at home, you have a shelf, and on that shelf, you have all of your most important possessions. Maybe you have a collection. Maybe you collect stuffed animals. And so you're like, I want to rearrange my stuffed animals, but I have like my special Webkins ones. And I have, do you remember Webkins? Okay. And I have like my Beanie Babies. They need to be together. And then I have, what would be another group of stuffed animals? Your Webkins, your Beanie Babies. And your third group is just whatever else. And you want to keep your Beanie Babies together, and you want to keep your Webkins together, and then you want to arrange them on your shelf so they're really pretty and nice. So the strategy of this, when they're grouped together, is we count how many groups we have, and first we decide how we're going to arrange that. Then we look inside of each group and arrange those ones. And it's kind of like spaces, because each of these is a decision. First you decide how you're going to arrange your groups. Then you go to your first group and decide how are you going to arrange them. So I looked at one of my collections of math books, of course. And let's say I had 5 or 4 different calculus books, 5 different algebra books, and 4 different geometry books. Okay? So sometimes the questions aren't super clearly worded, and can you see how you might get this? Oh, 4 calculus books. Are they the same? Are they identical? You might think of it as an identical object. So grouping questions, because things are in a group, which makes them similar, you have to decide, is this a grouping question, or is this an identical objects question? If it's a grouping question, I have 3 groups. So that's my very first space. Underneath it, I can write groups. I know I have 3 groups. You can arrange 3 things in 3 factorial ways. Then let's say I put my calculus books first. Well, I have 4 calculus books. 4 calculus books could be arranged in 4 factorial ways. My next decision, how am I going to do my algebra books? That would be 5 factorial ways. And finally, my geometry books, another 4 factorial ways. And since it's like spaces, each of those decisions gets multiplied together. So anytime we're grouping things together, we're going to use a grouping strategy. Number of groups first, then look at each group separately and figure out how many there's going to be. All right. So here is our second grouping question. We've got 5 people. Amy, Bill, Jill, Lee, and Tom are at the park bench. How many ways can they be seated if, Jill and Bill want to sit together? It's so nice. So it's a grouping question because you have to put Jill and Bill together, and then you still have Amy, Lee, and Tom. How many groups? Okay? Number one mistake here is people say 2 groups. Do Amy, Lee, and Tom have to stay together? Or could Jill and Bill be in the middle of them? Jill and Bill could be in the middle of them. You just have to keep Jill and Bill together. The rest don't matter. So when we go to our groups here, we would say there are 4 groups. Sometimes in these people questions, people actually consider this like, this is one person. Has there ever been like a couple at the school here where you're like, you never, ever, ever see them apart? They're like, when they're at school, they are always together. And when it happened, like I remember growing up, one couple, it was Derek and Carrie, we just called them Carrick. We had a single name for them. Like, this is the Jill Bill. They're never apart. So you could think of this as 4 people. How many ways could you arrange 4 people instead of, but it really is 4 groups. Then when you look at each group, there's the Jill Bill group. Monday, Wednesdays, Thursdays, they hold right hand, left hand. Tuesdays and Thursdays, they hold left hand, right hand. So how many ways could you arrange them? 2 factorial ways.
You said Mondays, Tuesdays, Thursdays, and Thursdays.
Oh, I meant Monday, Wednesdays, and Fridays. Monday, Wednesday, that's right hand, left hand day. And then on Tuesdays and Thursdays, they're gonna switch it up, right? And then you could do Amy, Lee. This is redundant, but so they don't feel left out. You could put 1 factorials there for those groups, even though there's just 1 in them. It's not going to matter. If we multiply this out, we're going to get 48 ways that they could sit together. Part B. Oh my, now Lee and Amy also have to sit together. Poor Tom. Don't worry, Tom gets his revenge in part C. But right now, okay, now you've got the Jill Bill, the Laney, and poor Tom. And you see that now we have 3 groups. So for our groups, we would have 3 factorial. The Jill Bill would be 2 factor. The Laney would be 2 factorial. And then you could write Tom all by himself there. You wouldn't need to. If we multiply this out, 6 times 2 times 2, get 24 ways. Now, something happens in the friend group, and the next time the 5 friends go to sit at the bench, we have the following scenario. Jill and Bill must not sit together. Lee and Amy, they're just fine. They could sit together. They don't have to. It's okay. But at this situation, I'm surprised they even came to the park bench anymore. But Jill and Bill are like, we are not sitting beside each other.
They came to the park bench for Tom, obviously.
I don't know. You can create whatever kind of scenario happened in your head. So this is a great example of the not strategy. It's actually quite complicated to think, okay, so Jill could be first, but then not Bill, and then Bill second, but Jill could be second. Well, there's so many different possibilities that would work, but counting them would be complicated. So this is where we really like the not strategy. And the not strategy is where you count all the ways and subtract the bad ones. Well, all the ways, 5 people on a park bench would be 5 factorial. The bad ways, we actually counted in part A. We counted that there were 48 ways where Jill and Bill were together in part A. And it wasn't that hard to count that. Then if you take the 120 and minus the 48, you will get 72 ways that they are not together. Our last strategy in permutations is called cases. Sometimes you try to count something directly or all at once, and it doesn't work. So you count it separately in different situations or different cases, and then just add it up to get the total. You did this, some of you got to the president secretary question on the whiteboards yesterday, where the president was male and secretary female, and president was female, secretary male, and then part C was how many ways were they in opposite, like could be either or. You just had to add A and B together. You were doing cases in that question. So how do we know it's a cases question? Well, this one says at most 3 different digits. So you're counting 3-digit numbers, 2-digit numbers, and 1-digit numbers. Those are hard to count at the same time, so we break it up with cases. And with cases, we write case 1 and a little description. So I'm going to start with 3-digit. Are there any restrictions when counting 3-digit numbers? Yes?
The first digit cannot be a 0.
This one is not a 0. So there would be 9 choices there. Then you've used up one number and 0 gets added back in. 9 choices there. And then you've used up 2 numbers, there would be 8 choices left for 648. Case 2. 2-digit numbers. Again, restriction, this is not a 0. 9 choices, and then how many numbers do you have left? 9 left. There's 81 2-digit numbers that are different. And then finally, case 1, or case 3, 1-digit numbers. Is 0 a digit? Would you say 0 is a 1-digit number? Yeah. So then we'd have all 10 choices, no restrictions on this one. So you couldn't count it all at once, but you could break it up into smaller things that you could count. And have I counted 3-digit, 2-digit, and 1-digit numbers? Yes. Add them up. And you would get 739 numbers where all the digits are different from 0 to 1,000. Which is kind of interesting because at the beginning of this unit, if I had said, how many numbers from 0 to 1,000 have all the digits different? Strategy would be like to start writing them out. This is kind of, would be an annoying strategy. Some of you might use the not strategy. Go, it's annoying to write them all out. Maybe it would be quicker just to write the ones out that are different. So you'd write out 11, 22, 33. But then it's like, oh, it's kind of annoying. Like there's 101, there's 110, 111, 112, 113, 114. Oh my goodness. And then there's a lot of those ones too. But now we've developed strategies where we can count complicated things relatively quick. A very common cases question happens when you have more than one restriction. So in this question, we want to use the numbers 1, 2, 3, 4, and 5. And we want our number to be bigger than 300 and also even. So we have 2 restrictions. In fact, if I write things out to start off with here, can you see that the restriction on the first digit, that the only possibilities are 3, 4, and 5. And if it has to be even, there's a restriction on the last digit, and the only possibilities are 2 and 4. And our strategy was, when there's a restriction, deal with the restriction first. But now we have two restrictions. So we go, okay, and I'll do this in red because this is going to be a problem. I would have three choices here. Right? I could pick any, a 3, a 4, or a 5. How many choices if I went to my second restriction and did that next? 2. Why is this a problem? Oh, but I might have picked a 4. So it's 2 or 1. Should I write 1.5? Well, but the 4 doesn't happen as much. Should I like put 1.3 repeated? This doesn't sound like it's going to be working out very well. We have a problem. We really don't know what number we can put into the second space because we might have picked a 4, but we might not have. Yes?
So we're going to have to use some cases.
We're going to have to use some cases. And you can choose. So when you're doing cases, you can either choose restriction 1 and break it up, or restriction 2 and break it up. In this case, I would probably take restriction 2 because it only has 2 options. So case 1, I'm going to first count all the numbers that end in 2. Well, if it ends in 2, this for sure is going to be a 2, and there's only one choice there. To be greater than 300, can you see that you would have either 3, 4, or 5 as an option there? So I have 3 choices there. Now, considering 1, 2, 3, 4, 5, for sure I've used up the 2. And I've used up one of 3, 4, or 5. I don't know which one. Maybe it was the 5. Maybe it was the 4. Maybe it was the 3. How many choices do I have left? I have 3 choices left. Okay? Just because you put a 3 in a space does not mean you used up all 3 of those numbers. The 3 stands for your choices. You had 3 choices and you chose one of them, which would leave you with 3 choices left here. So there are only 9 numbers greater than 300 that end with a 2. Case 2, what haven't we counted? We haven't counted the numbers that end with 4. So now if this is a 4, one choice there. If it has to be bigger than 300, you see that now you can only put a 3 or a 5 as the first digit because the 4 has been used up. So I deal with that restriction 2 choices. So if we imagine the numbers 1, 2, 3, 4, and 5, for sure we've used up the 4, and now we've used up either the 3 or the 5. We don't know which one, maybe the 3. How many choices do we have left for that middle space? 3 choices left. Case 2 has 6. Add up your cases. You would get 15 ways. You would get the same answer if you did 3 cases and said, I'm going to start with a 3. Count all my 300 numbers. Start with a 4. Start with a 5. And sometimes people do, like, can you see, you could do a case where you say, I'm going to start with a 3 or a 5. Because really the problem is the overlap of the 4. That's what's causing the issue. If I choose a 4 here, I can't choose a 4 there. So, if you break up your cases to deal with the issue, you could do a case where you start with a 3 or a 5, then you could end with a 2 or a 4. And then do the case where you start with a 4, then you would have to end with a 2. And your numbers will be different. You'll get 12 and 3, but they'll still add up to 15. So, there are 2 very typical ways that you will run into cases question. One is like this, where the restrictions overlap. And the second famous cases question looks like this. Can you count how many numbers are greater than blah, blah, blah? Okay, this is still 1, 2, 3, 4, and 5. If you notice how this question is written, this is part B. It doesn't have to be even. It just has to be greater than. So if you try to do it all at once, so I'll do this in red again. If I try to do it all at once, I have a restriction on the first one. It obviously cannot be 1. Can you see that the possibilities for the first one are 2, 3, 4, and 5? I'll do this in red, because this is going to cause us problems. There's 4 possibilities for the first spot. But now I run into a problem with the second spot. Can I put a 1 in the second spot? Maybe. When can't I put a 1 in the second spot? If I picked a 2. So we run into a, oh, I don't know what number I can put here, because that number would depend on what number I put first. So I like to do sort of my method for solving these greater than questions is I always make my case 1, looking at the problem, here's the problem is in the first space, what would guarantee that it would work, that I'd have no restrictions? Can you see that if I started with a 3, a 4, or a 5, here's my 3 spaces, if my first number is a 3, a 4, or a 5, and gives me 3 choices, that would count numbers in the 300s, the 400s, and the 500s. That would guarantee, doesn't matter what I do after that, I'm guaranteed to be bigger than 232. So if I guarantee that this one is going to be something that works, no restrictions. How many numbers do you have left? You've used up 3, 4, 5, maybe the 3. Can you see that if you chose one of those, you'd still have 4 numbers left? So you would have 4 choices there. Now you've used up 2 numbers, 3 choices there, for 36 in total. Case 2. What didn't I count? I didn't count start with a 2. Now if I start with a 2, the second number could be a 3, a 4, or a 5, but the 3 still causes problems later on. So again, what would guarantee that it would be bigger if I started with a 2 than a 4 or a 5? This will count all the numbers in the 240s and 250s. And if I have numbers in the 240s and the 250s, they're guaranteed to be bigger than 232. So I have 1 choice there, 2 choices there. How many numbers are left? 3 numbers left. For 6. What haven't I counted now? The numbers in the 230s. So case 3, start with a 2, then a 3. So this has to be a 2, 1 choice. This has to be a 3, 1 choice. And now I'm counting numbers in the 230s, and there's going to be restrictions on my last number as well, because it has to be bigger than 232. And anytime there's a restriction, it's good to write them out. Because there are 3 numbers bigger than 2, but do you see that you've already used up the 3? Do you have any? Okay. Yep. So as a result, there are 2 here. And add up yours. Add up the 3 cases to get 44 ways in total.